problem that you might not have understood, that I feel that in one slide there was one signal, that is b to the power mod n. Okay, so it is this signal. So b to the power mod n, actually I am just talking about the plot, how the plot looks like. B to the power mod n means when it is n is positive, so the signal is b to the power n. Okay, so if b less than 1, so each time the n increases, the value, instantaneous value, get decreased because b is less than 1. Say point, if b is 0.5, so first at n is equal to 1, so it is b to the power 1, that is 0.5. At n is equal to 2, b square, so 0.5 into 0.5, it is 0.25. So each time it is decreasing. Similarly, the negative side, the doubt is it is b to the power minus n. Okay, the signal is b to the power minus n, and actually this will also decrease because n is negative. So when n is minus 1, so that time b to the power minus n, so b to the power minus of minus 1, so it is b to the power 1 only. The next value n is equal to minus 2, so it is b to the power minus of minus 2, so it is b square. So it is also 0.5 into 0.5, so 0.25. So this way the signal decreasing in both sides when n is positive and when n is negative. Okay, so that is the doubt I thought you might have not understood regarding the during the discussion. So, and this example is sometimes this kind of examples comes in the competitive exam. I have seen in some question paper. Plot the b to the power mod n. It is the plot like this. Similarly, b to the power mod n when b greater than 1, and b to the power mod n when b less than 1. So these are the two good examples. Okay. Now coming back to the topics that I wanted to discuss today, that how the Z transform is used to solve difference equation. Okay. So difference difference equation we have seen by finding the homogeneous solution and particular solution. Now another method, it is the indirect way, but it is very easy method to find the solution of difference equation. So first step is apply Z transform to the difference equation. Then the initial conditions you have to apply, and then you have to find, once you get the expression in Z in terms of Z, then apply some partial fraction method. Okay, then you get the apply the inverse Z transform. Okay, so you'll get the time domain equation. So let us see the formula. That one example we take, yn is equal to 0.1 yn minus 1 0.2 yn minus 2, that is equal to xn plus xn minus 1. Okay, so what the question is, determine the input impulse response yn, determine the impulse response yn due to the impulse sequence xn is equal to delta n. Okay, so now let us solve it. So first we have applied the Z transform over this equation. So it is yn, then it is yz, then yn minus 1, it is 0.1 into yz, z inverse. Okay, look the property that we have used, that is delay property. Okay, delay property is y of n minus 1, if it is there, then you have to the amount, the delay is there, so you keep it on z power, the power of z, so it becomes z to the power minus 1, and it is y. Then next value is minus 0.2, so it is y of z, yn is there, but delay is n minus of 2, so it is z to the power minus 2. Okay, z to the power minus 2, and so this is yz. Similarly, xn, z transform xz, and x n minus 1, then z transform is xz, but since delay is there of 1 unit, so we have to apply z inverse. So this is the property. According to the property of z transform, we have to use this. Then just follow the steps, apply, then you take common yz, you take common, so it becomes this one, 1 plus 0.1 z inverse minus 0.2 z to the minus 2, and xz 1 plus z inverse. Now this xz is actually what it is. It is what since it is xz is what z transform of input xn. Input is what? Input is delta n. So the z transform of delta n is 1. So in place of xz we write 1. So we get yz is equal to this by this by this. Okay. So once we get yz, then once we get yz, okay, this is yz. Then you just apply. Then you convert it into positive power of z. Positive power of z by multiplying with z square. So we can find the roots of the polynomial of numerator as well as denominator. So you get this, and according to the process of partial fraction, okay, so we get it yz by z. This is the way we always do to find the partial fraction method, yz by z. So it is z plus 1 divided by z minus 0.4 plus z into 0.5. So we get this value. Okay. So we have to get the coefficients a and b, but with poles at 0.4 and minus 0.5. So you find the value of a and b, and we get yz. This. So once we get yz, then it's directly will be able to get the you have to apply the transform. Inverse z transform is what? According to the formula of according to the formula of 1 by 1 minus az inverse. Okay, 1 by 1 minus az inverse. So actually, if it is the z transform, then its time domain signal is u of alpha to the power n un. Okay, alpha to the power n un, and 1 by 1 minus az inverse actually means z by z minus a. Okay, z by z minus a. Now this z by z minus a, this z comes from the left hand side. This z goes to right hand side, from left hand side to right hand side. So it is a into z by z minus 0.4 and b into z by z minus 0.4. So now this according to the inverse z transform formula, that 1 by 1 minus z by z minus a actually a to the power n un. Okay. So this way a is in this case 0.4 for the first part, 0.4, and for the second part a is minus 0.5. So it is a causal sequence. Okay. and we get alpha to the power n un or a to the power n un or alpha to the power n, whatever it is. So 0.4 to the power n un with their coefficients and minus 0.5 to the power n un. So have you understood this example?
Yes, sir.
Okay, very nice. Then another method is how to find the step, how to find the response of due to unit step function. Okay, in that case, xn is unit step function, so its z transform is z. I told you that z by z minus a is a to the power n un. Now a is 1, so 1 to the power n un would be the time domain signal in that case. So 1 to the power n means 1 only. So it is for positive value of n, it is obviously 1, not negative value of n. So that's why we directly write that z transform of un is valid for positive values of n only. So that's why z transform is z by z minus 1. So the same way that we did that for the previous case, we now find yz as this. In place of xz, we write z by z minus 1 and the remaining part is same. So we get another extra additional term, that is pole at z is equal to 1. So we find three terms, okay, but their coefficient will slightly differ. So we get three terms, okay, and accordingly we write the we apply inverse z transform. Yz we get after partial fraction expansion, and we apply the inverse z transform. So we get 2 un minus this coefficient minus 1.0370 to 0.4 to the power n un and minus 0.5 to the power n un. Okay, so this is the very easy method. No need to go through the big process of finding homogeneous solution and particular solutions. Okay, but that is the direct method. But here the one under here one with the easy method is that Z transform we use. Okay, and apply partial fraction method and after that inverse Z transform. That is the simple steps. Okay, so now you can see other examples like if some initial condition is provided, initial conditions. So y minus 1 is equal to 1. Okay. Then what will be the solution, okay, for this difference equation? So it is performed like this, that taking the z transform of both sides, okay, we get yz, then 0.5 0.5 y of minus 1, okay. Yeah, they have calculated the z transform of this signal, okay, 0.5 y of minus 1 z inverse y of z. So actually, say if some initial condition is present, that time you have to go through this process. If no initial condition is there, then directly you could have you could write that is 0.5 into z inverse into yz. Okay, directly you could have been you could have you could write. Okay. So and the right hand side it is 5 into z transform of this function. Okay. So you know that is z by z minus 2, z by z minus 0.2. So that is written there. So already it is y of -1 is given is equal to 1. Okay, so it is also very good example. So if no initial condition is given, then directly the Z transform of the 0.5 y of n-1 would have been Z inverse yz. But since this is there, y of -1 initial condition, so you could just find this way the Z transform, that n is equal to 0 to infinity, okay, Z to the power -n. So it is when n is equal to 0, that time it is only y of -1. So this way we can write, just there use the formula. Okay, initial value is coming here. Then Z inverse of all these terms. Okay, then actually this term represents y of z. Z inverse y of z. So then the other process are same. Partial fraction expansion is calculated. Then the coefficients a and b are calculated, that you know the process, and then you apply the formula for inverse Z transform. Okay. So have you understood this problem?
Yes, sir.
Okay. Very good. If you have any doubt, you can ask. Should I repeat again the process?
No, sir, it was clear.
Okay, fine. Okay, then this topic is over. Okay. Then I have uploaded already this slide, module 1, part 3. Then we go for another PPT, that is, yes. Is the slide clear, visible?
Yes, sir.
Okay. So now we move to Fourier transform. Fourier transform from discrete signals. So there are topics like discrete time Fourier transform, discrete Fourier transform, okay, fast Fourier transform. So this will be discussed. Now, these are the you see that what we mean by Fourier series. Fourier series actually is applicable for periodic signal, but discrete time periodic signal, discrete time periodic signal. Fourier series actually is meant for periodic signal. Maybe the signal may be continuous or discrete. So the Fourier series for discrete signal is called, the Fourier representation for discrete signal is called discrete Fourier series. Okay. So there are two parts. So you know that any signal can be represented in terms of sine and cosine term. Okay. So the exponential Fourier series, okay, that is represented as with some coefficients ck, okay, into e to the power j 2 pi k n by n, where n is the period of the periodic signal. Okay. Similarly, the coefficient Ck is the magnitude of each and every cosine component. Okay. So, and actually represents the Fourier series representation, okay, of the time domain signal xn. Xn is time domain signal, and Ck is the magnitude of the Fourier of each cosine component of the present in the signal. So this next we see that what do you mean by discrete time Fourier transform? Okay. So the general formula is x of n e to the power minus j omega n. Okay, and n goes from minus infinity to plus infinity. Okay, then that you can see that xn is your time domain signal. It is the Fourier transform of an aperiodic discrete time signal. That is the important thing. Okay, important thing. That previous one was for periodic signal and discrete time Fourier transform Dtft. You can see from the name that discrete time signal, and it is periodic signal xn. So that means it has some length. Okay, length of sequence. The sequence length of sequence is not infinite, it is finite. It may have some few number of samples like L, number of samples may be L or maybe M, okay, like that. So it is a constant or finite. So in that case, the Fourier transform tells that it should be x of omega, that is equal to summation n is equal to minus infinity to infinity x of n e to the power minus j omega n. Okay. So x of n is your time domain signal, okay, and e to the power minus j omega n, where omega is what? The frequency variable. Okay. Frequency variable is omega. So it is discrete frequency, not the frequency for continuous time domain signal. So that's why omega, the range of omega will be what? It will be minus 0 to 2 pi, okay, or minus pi to plus pi. Okay. So x omega represents the frequency content of xn, and important thing is that x omega is periodic with period 2 pi. Okay, that is very important. So this periodic signal, it is a, since it is aperiodic signal. Okay. If you take the aperiodic signal, its Fourier transform will be periodic. Okay, that means there will be harmonics. It is repeating, the frequency will be repeating. Okay. So it is periodic. Okay. Each time the frequency, the same the same frequency, but multiples of that frequency would be there. Okay. So it is what harmonics would be there. So here some properties describe that why it is periodic with period 2 pi, because if you uh, add frequency 2 pi with omega, omega plus 2 pi or 2 pi k, any multiples of 2 pi, any multiples of 2 pi, then it becomes, in according to the equation, that e to the power minus j omega plus 2 pi k into n, then it is, we take e to the power minus j omega n and e to the power minus j 2 pi k n, and e to the power minus j 2 pi k n is actually what? Cos of 2 pi k n. Okay, so cos of 2 pi k n plus sine of 2 pi k n. Okay, it is actually what? It is 1. So we get that it is same, it is equal to 1. So cos 2 pi 0, it is 1. So and sine 0 it is 0, sine 2 pi it is 0, and cos 2 pi it is 1. So it is this term to the power minus j2 pi k, and it is 1. So it is now delay not required there. So it is no change in the signal. So it is actually x of omega. So multiple of frequency we get. Okay. So our frequency are repeating. So in this case, there are two things, that one is inverse Fourier transform and direct transform. So if it is direct transform, so it is x of omega. It is convert xn in time domain signal, in frequency domain it is x of omega, and formula is n is equal to minus infinity to infinity. Okay, this is also means it is periodic but range from minus infinity to infinity. Okay, discrete time Fourier transform. Discrete time Fourier transform is the Fourier transform for aperiodic discrete signal. Okay, and frequency and time, yes, time range from n is equal to minus infinity to infinity. Okay, and omega also periodic. And in case the inverse transform is 1 by 2 pi x of omega j omega and d omega. Okay, this is the formula. Synthesis equation and analysis equation. Analysis equation is called direct transform. Synthesis equation is called inverse transform. Then the important things that is present with every Fourier transform is the Dirichlet condition. Okay. That tells that the signal should be summable. Okay. So xn, summation of xn should be less than infinity. Okay. So that means should be finite. So according to this this thing, that x omega, then the summation of the frequency domain of this one, that should be finite also. Okay, summation of this one. So some example we take, that x omega is this one, it ranges from minus omega to plus omega c, minus omega c to plus omega c. Okay, it is 1, and outside that it is 0, and it is repeating. You see, it is repeating. So repeats after 2 pi. Okay, so x omega is omega c. Omega is when omega is less than omega c, this is the omega variable, x-axis. When omega is less than omega c, plus or minus whatever it is, then it is 1, and outside that it is 0. Okay, so means within omega c to omega pi. Pi because it is discrete frequency variable, so that's why frequency ranges from minus pi to pi. Okay. So now, how to find the inverse discrete time Fourier transform? IDFT means inverse discrete time Fourier transform. So you just go through that, apply the formula for inverse discrete time Fourier transform. So you know that is a rectangular function. So what is the inverse Fourier transform of rectangular function? Do you have any idea?
Sir, sync function.
Sinc function. Okay, so we get sinc function there. Okay, as it is followed according to the example. Okay, so but its magnitude at n is equal to 0. Okay, is equal to omega c by pi. So we get omega c by pi. Okay. So at so time domain signal we get that at n is equal to 0 it is omega c by pi, and outside that it is actually sinc function. It is actually belong to the part of sinc function, that omega c by xn is what? Sine of omega cn by pi n. Okay, sine of omega cn by pi n. So we now there are some examples of DTFT. Okay, so we take the function is less than 1. So what is f of, then directly you go through this example and plot the figure. You see very important thing that your time is showing pictures. Okay, comparison part you just go through it how it is derived, but the picture is what inference we draw, that a is less than 1. So a to the power n, it is a decaying signal. Okay, so it is um, so we get it. No. It is a to the power n that earlier we discussed. That a to the power mod n. This is this signal. A to the power mod n. It is event signal. Okay, event signal or symmetric signal. So its Fourier transform is this one. Okay. Fourier transform is 1 minus s square. Okay. We just go through this process, how they have calculated, and it is the thing that it is continuous signal. The discrete signal is not time domain frequency domain is continuous. 4 pi like that, both in positive and negative. But since it's a cosine graph or something else, so omega is not discrete. Omega take any values and it is continuous, so its graph is continuous. So when we calculate the discrete time Fourier transform, okay, of a periodic signal, its Fourier transform would be periodic, and is the important thing, continuous.
Sir, excuse me,
Then
sir.
Your voice is
Sir, your voice is a little bit distorting, sir. I didn't understand why we get a continuous call there.
we calculate the discrete time Fourier transform. So according to the formula, summation of this xn e to the power minus j omega n. Then after calculating this summation of this, you find this as series. Okay, series one by, and series converts to this series left hand side where I'm rotating the mouse, moving the mouse around. If this series converts to 1 by 1 minus a to the power e to the power minus j omega plus a into e to the power j omega divided by 1 minus a e to the power j omega. And if you calculate this, then you will find that 1 minus a square, 1 minus 2a cos omega a square. Okay. So this is what? This is a cosine function. Okay. But some other this things are there, other factors are there, but it is periodic because it involves the cosine function, and it is continuous because no terms n is there. Okay, this omega, it is dependent on omega. Is a plot between omega and x of omega. X of omega is what? This is this term including cost function. Okay, and omega is continuous. Omega is not discrete. Okay, omega is continuous, discrete frequency variable. You see, it is the range. It ranges from 0 to 2 pi or 4 pi. Okay, in positive side or negative side, 0 to minus 2 pi, minus 4 pi, like that. So it is continuous. Understood?
Yes, sir.
Okay. So now another example. Many examples are written, and very important. Always rectangular pulse is comes. Okay, in every examples. Like if it is a rectangular pulse xn, okay, then you see that x of n, okay, it is a finite length sequence. That is, it is 1 for 0 to n1 and 0 to minus n1. Okay, and other than that, it is 0. So this is the samples. If I have plotted here, okay, few samples are there up to n1. When n is positive, that is 1 for 0 to n1, and when n is negative, that it is range from 0 to minus n1. So in that case, that you see it is calculated as minus n1 to plus n1 to the power j omega n. So if you use thus, you know that how to calculate this way, this type of functions. So it is actually sinc function. So if you get this one, so you will plot, you will get this kind of function. Okay, it is omega variable plot omega, and it is continuous because omega is continuous, and is periodic because it is a sinc function. Okay, means it is this sine of omega. Okay, sine of omega term is there, so that's why it is periodic. Sine of omega n1 plus half by sine of omega by 2. Okay, so it is periodic, and this is the plot. So you just go through some property of discrete time signal, okay, and we'll tell some things about this. So today now time is over. So now I stop here, and if possible I can take the class in the next tomorrow also. Although tomorrow is holiday, okay, I can take the class. I am not sure. Okay.
Sir,
So
actually, I got a notice, sir, that tomorrow's holiday
shifted
shifted on
to
Saturday.
okay, notice is there.
Yes, sir. Thursday holiday shifted on Friday, sir.
So Thursday holiday shifted on Friday.
Yes, sir.
Okay, okay. So okay, in morning, what time you are free?
Sir, tomorrow we are not free because we have classes. Already we have one class, sir, which was scheduled in afternoon. We are having in the morning only.
Plus
Okay,
tomorrow
okay.
is lab, sir.
Tomorrow?
Lab.
Tomorrow signal processing lab, sir.
Okay, tomorrow first time, yes, yes.
Yes.
Sahu sir will take because I am not present there. Okay. So let's see. If possible, I can take in the second half. Okay? Okay.
Yes, sir.
Thank you.